Okay, I'm going to be presenting my students Igor's master thesis on types embedding of miniKanren into Haskell. Our aim was to empower the functional conversion, and after the last brilliant talk, I feel a little bit embarrassed because this is like a baby version of what Santiago has just said. So don't be very don't expect too much. I'll start from the very beginning, from talking about functional conversion. So in the world without miniKanren, everything is very sad, and for each task you have to create a program. If you want to find all of the reachable vertices in a graph, you need to write a DFS. But then, if you want to find the path, you need to write a DFS, but with a little bit of the tweaks. And then you want to find all of the paths, and you also need to write some program, and it is exhausting. In the world with miniKanren, you don't have to do all of that. You just write one relation, right? You start with a description of what you're trying to find. You encode it as a relational program, and then you query it in order to find one path, find all paths, find all of the reachable vertices, and stuff like that. And this is really brilliant, and this is something that we all enjoy, I hope. And it powered this idea of creating solvers from verifiers. Basically, the idea is that it's really easy to create a function or a predicate that checks that some property holds for some data, right? But for example, for isPath, it's just this tiny function which can be really easily translated into a miniKanren and then run whatever. And it's much more complicated to find the data that makes the verifier ticks, right? And we don't really want to do that. We want to use miniKanren and all that we have in our power to avoid writing solvers ourselves. Thankfully, it exists. It allows us to view a program as both verifier and a solver. And we, of course, can have compilers and decompilers, evaluation and program generation, like type checking and type inhabitants duality, all empowered by miniKanren. And what is the issue with that? Of course, the issue is that it times out very fast. There are a lot of reasons why it happens. And in our research, we focused on the two aspects. The first one is the unifications are expensive, and the second one is that the order in which goals come in the conjunction is very finicky, and it really depends on the direction you want to run your program in. Of course, there are some ways to help with that, and for us it is a specialization. Specialization is a general approach of creating programs which run faster based on some data that is known statically. For example, if you have a function that implements a power function, and then you know that in your program you only compute power base 5, then you can specialize that program. In some cases you can do this automatically. Like this general approach was created many years ago, and the idea is just to generate the program that runs on the same dynamic, unknown statically data as the previous one, generating the same outputs. In miniKanren, we of course have this same idea, where sometimes we know some arguments. For example, here in the forward direction, we know two vertices between which we search for paths. In this case, we generate vertices which surface beginning and the end of the path, and we run in the backwards direction. But in some cases, we don't know the values of our arguments. We only know the direction in which this program is going to be run. For example, in this case, we know that A will come from somewhere, and we know only that. And we can use this direction information in order to specify the program and make it run a little bit faster. This can be seen in some examples. For example, here we have a sorter relation that sorts a list and function as a sorter in one direction and as a generator of all of the permutations in the other direction. Unfortunately, there is no way to write this program in such a way that it works in both directions. We can only reorder the last two goals based on the known direction that we want it to run. And this is something that specialization for miniKanren is doing. It really, like, knowing something about the mode, it reorders the conjunctions in a way that makes sense, hopefully. And even that is not enough in the majority of cases. As I said, unifications are expensive, and getting rid of as many unifications as possible is one way to fix this problem. So what we did, we created the functional conversion, which takes a relation, and then it basically compiles it into a function that gets rid of all of the unifications that exist there. So it takes care of this knowing the direction. So specialization, in the end, we decided to use specialization only for known arguments, but the direction is encompassed in the functional conversion. In our implementation, we dump our functions into Haskell or Camel or whatever else functional language you want. But I'm going to be talking about Haskell because Haskell is the best, right? All right, so let me go through some examples. This is an example of an addition relation that runs in the backwards direction. So we give our program a sum, and then we expect it to create a factorization into summands. This direction is non-deterministic. When you have non-determinism, you cannot easily provide a function that generates the result, because functions are inherently deterministic, right? So what we do, we instead use streams to express this non-determinism. These streams are something that is like the base pillar of any miniKanren relation, and this is something that survives our functional conversion. This is a part of miniKanren that we preserve. So, not going into too much details, we can see that our functional conversion works as it converts every disjunct within our programs into like a stream, and then it concatenates them with M+. So the first case, of course, provides that x is always 0, and z is whatever y is, right? So we returned it as a result. In the second conjunction, we need to do this recursive call, and then we return the result of it. And z is unified here with successor of some value, and this is translated into a pattern match. So basically what we are doing is we classify every single unification in our program into either equality check, pattern match, or a constructor applied to something. And there is, of course, a fourth component, right? What if we cannot classify it into either of these three things? What if we unify two logical variables? This can be exemplified by this direction, where we have only the first argument known in the addition. And here we generate the infinite stream of values, right? How do we represent it? In miniKanren, you use this underscore dot something to represent a logical value, but our goal was to get rid of that at all, completely. Logical variables is something that shouldn't exist in functional programs because functional world doesn't know how to deal with it, right? So as a solution to this, we provided the idea of generators. A generator creates a stream of all possible values that your variable can take, being like a free logical variable. And then we use it to generate our streams of results. And this functional conversion was implemented. It worked somewhat decently, but the issue was that it was implemented over a deep embedding of miniKanren into Haskell, which basically like started with a parser, constructed an abstract syntax tree, and then did all of the steps of functional conversion, which doesn't really matter right now. But the thing is that our untyped deep embedding was terrible. It didn't have any information about types. We didn't have any data type definitions. We just knew that constructor started with an uppercase letter. We didn't have any static checks. We couldn't even check that a given relation was implemented somewhere in the program. It was impossible to extend this language completely. So it was a pain to work on the functional conversion over this embedding. As one of the very clear issues with it came these following two problems. So the first one is, since we didn't know anything about the types of the variables, we could only create a monolithic term type to represent values. Because if you don't know the information, where can you get it, right? And this monolithic term type, of course, suboptimal, to say the least. You could create stuff which doesn't make any sense, for example, as of nil and stuff like that. And you'd be surprised how easy it was to shoot yourself in the foot having this crutch instead of the normal types. The second thing was, since we didn't know anything about the type a variable had, we couldn't figure out what generator to use. And in this case, we just decided that the user is smart enough, they will figure it out. They will figure it out, but it will take them a lot of time. And one crucial thing is that we implemented all of that in Haskell, and we just threw away every single positive aspect of Haskell that exists there, right? We didn't use any information about types. We didn't use any of the static checks that it provides. So instead, what we tried to do next is to create a typed shallow embedding, right? And the requirements to it were threefold. So first of all, we needed typed terms to get rid of that monolithic term type and to empower the implicit generator passing. Secondly, we wanted it to be shallow in order to adhere to one of the miniKanren core principles, namely to be able to extend the language itself. And also we wanted to take advantage of the Haskell type system as much as possible. We also wanted to have access to the AST. So we wanted to be able to reorder conjuncts. We wanted to inspect unification, to figure out where we have values, where we have variables, where we have something partially defined. And also we wanted to have access to relation names and variables. Of course, there are multiple ways to do that. And there are at least 3 types Haskell embeddings that I know of, but now at least. When we first started, we just couldn't make it work with our functional conversion specialization pipelines. So we decided to do our own. Our own is not as beautiful as the Walrus's one, unfortunately, but it looks like this. It also has the disjunction implemented as a sum of some conjuncts. Conjuncts are basically expressed with do notation and stuff like that. We have some small inconveniences, such as we want to create a name for our relation. We want to explicitly say that we are calling the relation, but it is a tiny inconvenience compared to the amount of good we got out of this embedding. How we did that? We started with the logic term type, which is very similar to what Santiago presented, where we have a type with holes in it that represent the logic variables. This, of course, is generated. In the end, it seems like a lot of boilerplate to generate logic term types, which we got rid of by using template Haskell. But this is the easy part. More hard part was to create the shallow embedding itself. And what we did is to use final tagless style. So if you're unfamiliar with it or if you've forgotten, this is the idea of representing your program without an AST, and every single evaluation, the semantics that you give into a program is given by implementation of instances of some type class that encodes the structure of your term tree. And what is nice about that is that you can easily extend it by implementing new type classes with new instances and get all of the beauty of Haskell into your EDSL. So the basic type class that exists in our embedding is the Kanren type class. It looks more or less like this. We can see that there is only 3 parts to our core language. So it's the unification, calling of relations, and fresh introduction of new variables. And disjunction and conjunction come from additional context. So disjunction is represented as a sum from alternative, and conjunction is represented by the applicative. And you may be confused, why applicative? It's monad everywhere, right? But the thing is, we wanted to be able to reorder conjuncts. And how would you reorder conjuncts in a monadic style? You cannot. So what we did, we switched to applicative. And the thing that you saw before that with do notation, we actually used applicative do. So don't be fooled about that. But it doesn't really influence the way that the programmer uses miniKanren, which is really fun for us. As a proof of concept that it works, we implemented several interpreters. So the first one was the normal evaluator for miniKanren, which took us a while, and we had to rewrite our implementation multiple times. But then the complicated part started, when we started to work towards the functional conversion. We tried to do the functional conversion, the whole functional conversion over this representation. It didn't really work. So instead, we dumped our representation into a normalized AST, and then we powered the functional conversion from it. Normalization itself was hard enough, and you can find the implementation details in our repository if you want. But what we did in the end is replaced this first block of string parser to AST with an embedded program in Haskell through normalization into AST, and then we dump it into the previous pipeline, generating functions in the end. Just to showcase how the functional conversion results changed after that. So here's an excerpt of a project that balances some tree. Doesn't really matter what it does, but you can see the monolithic type here, which is ugly. And you also see that we have to thread these 2 generators here. And this generator is not even used in the balance program. Instead, it is used in a depth relation, which you just have to thread all the generators through it. And it is really easy to screw it up, mix the order or something. And this all went away when we went to the embedded DSL route. Now we have separate types for separate types for separate values. We don't have any generation. Generation is implicitly computed. It's basically Haskell compiler finds a proper generator among those that exist based on the type of the variable, and we don't really have to deal with it anymore. All right, I think that is it from my part. There is an implementation, there is of course a paper. Check it out, play with it if you want, and reach out to me or Igor with your questions or concerns. All right, thank you.
All right, we got time for some questions.
Can you hear me? Yeah. This is great, and I understand how this will make it so much faster if you remove the unifications. What I don't understand is how you put it back. So if I have a function that does addition, and now I do the functionalization, do I use that back into my relation? Does it dynamically send me to the right function?
There is no going back from the function to from a function to a relational program. So there is a converter which can be run over the function to create a relational program, and then we deal only with the relational program, and then we like transform it back into a function that works in the direction we want, basically. And this is like one-way street.
Thank you. As far as I understood, you're dealing with generators, and this generator can produce infinite number of results, right? And then these generators can be combined as a result of functional conversion, so you have a composition of these generators, potentially.
Okay. Okay.
My question is if this composition preserves the completeness.
As long as the generator is a stream, it should work fine, right? Because the stream is the...
Interleaving.
Huh?
Interleaving.
Yeah, interleaving stream, of course. This is the stream which is just from miniKanren'. It's stolen from miniKanren' completely. This is the same thing that we will use in the interpreter of miniKanren'. Yeah.
Okay, thank you.
This sounds like a hack, but it works. Yeah, because like the first iteration of these generators was using lists, and of course when you have lists, it doesn't work. It preserves the completeness, and this is why we preserve these streams in the function, even though they seem foreign.
Can you say anything about the performance differences that you found in using modes?
What we found. Let me say this thing. So basically, what we generate in the end is the function that is the same as the previous one, right? We just got rid of some of the small things that we have to deal with manually. So the performance didn't improve by using this typed embedding, as opposed to like the deep embedding and the functional conversion. Functional conversion itself improves the behavior of the programs somewhat. Yeah.
Can you go to the slide with where you changed your parsing to a normalizing parser? Because I missed a step here. There's normalization going on both before and after the AST. What did I miss?
This is not you who missed something, this is I who missed something. I just wanted to show like the big beautiful picture when only one block changes, but I should have changed two, right? Sorry about that.
No, I got to ask the question. That fully resolved.
I mean, we can dump it into a normal AST, the old AST before normalization, but it doesn't make any sense. We just combined them together as an exercise, actually.
And I have another question. Where are you sending him to grad school?
Sorry?
Where are you sending Igor to grad school?
Oh, this is a good question.
You can't turn that back on me. All right, let's thank our speaker one more time.